this video, we're still looking at the inverse function. We're going to look at some properties of the inverse function. The learning goal for this one is that, and we've done some of these before, but we're going to expand on it a little bit. I can find the graphical representation of the inverse of a function. I can find the numeric representation of the inverse of a function. Numeric representation is the equation. Of the inverse of the function. And I can state, this one's going to be new, I can state the restrictions on a function that would make the inverse a function. So we kind of alluded to in the last video that every inverse may not be a function, and we're going to see that coming up today. Okay, we've got our function up here. F of x equals 1/2 x minus 1 squared minus 3. This is quadratic, and we need to find the inverse. So remember, when we're doing this, we can think of this as a y. We're going to swap places. So I'm going to put x equals 1/2 y minus 1 squared minus 3. Okay, so now I have to bring all this stuff to the other side. I'm going to start by bringing this minus 3 over to the other side. It will become plus 3. Now the next thing, I can't get rid of anything in here because it's all tied in by this squared up here. So I'm going to multiply both sides by 2. So I've got 2x plus 3 is equal to y minus 1 squared. And now I'm going to square root both sides of these to get rid of this 2 up here. So if I square root this side and square root this side, I'm left with y minus 1 over here and the square root of 2x plus 3. So when we square root, usually we're thinking plus minus. Not always the case with these, if we remember from last unit. And then I have to add 1 to both sides. And I'm going to put the 1 out front here, although we like it at the back, just so it doesn't get confused with being under this root sign here. 1 plus or minus square root 2x plus 3. We could have put this plus 1 over at the back here. This is our vertical move up 1. So what this is saying is our inverse function is equal to, and maybe I'll put it at the end there so we're not confused, the square root of 2 times x plus 3 plus 1. So in this radical here, the square root of x, we would take the original function, square root of x, we would move it up 1, move it left 3, and then do a horizontal stretch of 1/2. Okay? So now we're going to graph each of these, and I'm going to call this up on some graphing software so we can see what it looks like. This here is this function up here. So this is And it makes sense if you think of your regular quadratic starting at 0, 0. We are moving it down 3, 1, 2, 3, to the right 1. There we go. And it's zoomed out quite a bit, but it is over 1 up a half right there. So there is this function here. Now if we look at the graph of our inverse function here, take both sides, so this is the graph of the inverse function with the plus and minus. So with this plus minus, if we take both sides of this graph, this no longer is a function. So is the inverse of this function a function? No, because if I do my vertical line test, I am now crossing this at 2 points. And I can do it at a whole bunch of times here. I can cross it almost anywhere, and I cross it at 2 points. Now the reason why it's in two different colors here is the blue is our positive and the green is our minus. Let's state the domain for f inverse x. We've got our domain, our x values are all bigger than 3. So the domain, we've got the set of x such that x is greater than or equal to -3, and x is an element of the real numbers. Our range for this is, right now our range is going up to infinity. This will keep going up, this will keep going down forever. So our range is the set of y such that y is an element of the real numbers. It can be all real numbers at this point. But we want to see how we might put some restrictions in on the domain of f of x so that the inverse is a function. Now if we wanted to restrict the original function, what we might do is we may just take half of it. So if we look at our axis of symmetry and either choose this side or this side, then when we swapped all the x and y values, it would just be one of these two sides and not both, and then the inverse would be a function. So if we put a restriction on this original function up here, saying we've got this function, but we're going to have the set of x such that x is, let's say, x is greater than or equal to 1, such that x is an element of the real numbers. And we can do this because, remember, the domain over here becomes the range over here. So if it's only everything greater than 1, and we've got this side here, when we move it over here, the range is going to be only everything greater than 1 over on this side. So a couple things to remember. The inverse of a function is not always a function. We may have to restrict the domain of f of x. So that the inverse is a function. Or I guess conversely, we could put some restrictions on the inverse. We could put some restrictions on f inverse of x, but these restrictions would go to the range. And to obtain the inverse of a function, we need to switch the x and y variables and solve for y. This is to come up with the equation. But when we're graphing, we're still switching the x and y variables. We just don't need to solve. We just need to replot those points. The range of f of x will become the domain of the inverse of x. The domain of f of x will become the range of the inverse of f of x. Okay, so there's a whole bunch of different properties that we can use, and we may need to do if we want the inverse to also be a function.